see, get this focused. There we go. Hey, welcome back to my channel. So we're going to be talking about the convolution theorem today and convolutions. I'm kind of trying to rush this video here because my children are quiet for a few minutes, and so I can actually record something. So the idea is that we're going to be defining a new kind of product, and this is called the convolution product of two functions. And the idea is that it can be defined as an integral where time is going backwards for one function and time is going forwards for another function. You take their product and you integrate it, and that gives you a new function that we call the convolution product. And what's nice about this special function that we're making, this convolution, is that it works really nicely with the Laplace transform. So what the Laplace transform does to a convolution is it takes the convolution and it takes Laplace transform of the convolution and it turns it into the product of Laplace transforms of the two individual functions you started with. And so that makes things a lot easier for doing things like inverting Laplace transforms. So what we're going to do in the real application of this is that we're going to, throughout solving initial value problems, we're going to end up with a lot of products of functions that we might not know actually how to invert directly. But we know how to invert like one factor versus another factor, and we can take advantage of that by using the convolution. So we're basically going to have, say, an unknown function g times some other rational function that we know, and we want to know what happens when we take the inverse Laplace transform of that product. And the way we do it is we take the one we know and we write down that function, which would be f. And say the unknown g of s we write as g of t, and we take the convolution, and ta-da, that is the inverse Laplace transform. And then anytime you get a new function, since this is an arbitrary g, just plug it into the convolution and you don't have to go through the whole route of Laplace transform solving the initial value problem anymore. What this also does is it allows us to investigate what are called integral differential equations. This is basically where you have y prime of t, or y of t is equal to what can be recognized as a convolution on the other side. And then basically if you take the Laplace transform of that, the convolution turns into a product. And that is one of the last points in this section, 7.8 out of Nagle-Saff and Snyder's 9th edition. And so we're going to talk about all of those. There's some extra stuff in there that in that section that goes a little bit beyond what we are going to be talking about in this lecture, and that's called the transfer function, which is connected to what's called the impulse response of a system. It's a good thing to know about, and definitely read up on it if you have the time. But unfortunately, we have to wrap up the class, and truly, there's no time to really communicate this idea. The convolution product is a simple idea, and it's nice to get across, and I really feel like you need this in order to round out your knowledge of Laplace transform. The transfer function is going to come up again if you go take, say, signal processing or control theory or any of these places, so this isn't exactly the last place you're going to see it. It'll also come up a bit in circuit theory, I believe. In any case, yeah, so let's go ahead and jump into it. Okay, welcome to class. So here we're going to be looking at section 7.8. You know, I don't like red, don't make it blue. 7.8, and this is the convolution properties of the Laplace transform. Right, so this is again in Nagle-Saff and Snyder, 9th edition. Okay, so the convolution theorem, well, convolution property. Basically the book starts off with this example where they say you take a look at y double prime plus y is equal to g of t for some unknown g. We know something else. We say that y of 0 is equal to 0 for the initial value, and we're also, just for convenience, also going to make y prime of 0 is equal to 0. Right, so this way we don't have to worry about subtracting off initial values at all. So if we take a Laplace transform of both of these guys, we're trying to basically come up with some way of expressing the solution to this problem. And so if I take a Laplace transform of both sides, what am I going to get? Well, remember, Laplace transform turns differentiation to multiplication by s. So here we're going to get s squared times big Y of s plus big Y of s is equal to whatever the Laplace transform of g is. All right, now what we can do is we can go ahead and factor out y of s, and it leaves us s squared plus 1 times y of s is equal to g of s. And
And then that tells us that what we are left with is y of s is equal to 1 over s squared plus 1 times g of s. So that tells us that y of t should be equal to the inverse Laplace transform of 1 over s squared plus 1 times g of s. And so, and whatever this is, value at t. So then the question is, how do we figure this out? So how do we write this in some way that's sensible? So we can't look up on a table because we don't know what g is, and so maybe this isn't like the cleanest thing to see right now. So what we're going to do is we're going to introduce this thing called convolution, and it's going to give us a very direct way of inverting a product of Laplace transforms like this. And so to start off with, let's write down what the convolution is. And so this is definition 9 in the book. And so they tell us that first of all we're going to have f and g of t be piecewise continuous on, say, 0 to infinity. And it says the convolution of f with g, I guess you could say, with g itself is a function, and is defined as, and so we're going to write it as f star with g at t. It is a function, and what we get is that this is the integral from 0 to t of f of t minus v, or nu, times g of nu d nu. And that's this operation. So turns out that this actually has a whole bunch of nice properties, and if you were a mathematician, these are all things you'd very much want to know. So for instance, first question you might ask, all right, so we're coming up with some weird kind of convolution thingy. It doesn't matter if f or g is first. And so the first thing is f star g is actually the same as g star f. This is actually not too hard to see. For instance, if I just take the integral from 0 to t of f of t minus v g v dv, and we go ahead and use a substitution, and I say let's make u is equal to t minus v, then that gives me du is equal to dt, or sorry, v is the thing that's changing here, so is equal to minus dv, and u itself is, and we can replace v by u minus t, and by t minus u. And then if we go ahead and plug all that stuff in, then we get the integral, we'll figure out the bounds in a second, of f of u g of t minus u du with a minus sign coming out. And if v is 0, like it is on the lower bound, then that means that u is t. And if v is t as it is in the upper bound, then u is 0. Now we have that minus sign, and that flips the bounds right back. So 0 to t, f of u, g of t minus u, du. And on the left-hand side, this was f star g of t. And on the right-hand side, this is g star f of t. So we see that it does not matter the order. This actually gives the same integral. Okay, so this is commutative property. Check. All right. What are some other things? So what we could do is we can say that f star g plus h, this is linear in each term. So I could go ahead and write this as f star g plus f star h. And that really just follows from linearity of the integral. So I'm not going to bother saying much more than that. The third thing that we can say, this is called the associative property. So f star g times h. This is equal to f star of g star of h. And that's not too hard to prove either. Just play with the definitions and dive into the integrals. And the last one is f star with 0 is equal to 0. And that's pretty easy to see, because if g was 0 all the time, then this whole integral is 0. So no mystery there. So the only thing I'm sort of leaving in the air is this associativity property. And that's not really too hard to prove. Just an exchange of integrals. But yeah. Okay. So that's the convolution definition and a few properties that we can exploit. So the big thing to take away is that it doesn't matter what order we take this in, and it doesn't. And if we have 3 of them, we're trying to convolve. You can convolve them in any order, and that's just fine. Okay, so that's really the takeaway from that page. Okay, so let's see what is important here. So the convolution theorem is really like what's really important here, and so and that's basically going to be, suppose that f and g are piecewise continuous functions from 0 to infinity of exponential order, so that each has their own Laplace transform. So we're going to say that f and g are piecewise continuous on, say, 0 to infinity, and of exponential order alpha. So this just means they have Laplace transforms, right? So what that means then is that we have a Laplace transform of f, and here we're just going to call this big F of s, and we're going to have a Laplace transform of g of s somewhere, and it's going to be called big G of s. Okay, so here's the cool part. What if we want to take a Laplace transform of f convolved with g? Turns out that is Laplace transform of f times Laplace transform of g. Okay, now why is this important? Well, if we go back 2 pages, we had 2 Laplace transforms multiplied by each other, and we were trying to undo it using the inverse Laplace transform. Well, it turns out if we know where this guy came from, and we know where this guy came from, then we can actually just take their convolution, and that is the inverse. And so that's the whole idea of this section. And so equivalently, inverse Laplace transform of big F of s times g of s at t is equal to the convolution of f with g valued at t. Nice and simple. Okay, so now let's go ahead and try an example. All right, so now we're going to try to use the convolution theorem to solve an initial value problem. And so we're back to almost identically what we had before. So in the section, we have a y double prime minus y is equal to g of t. And we're left with y of 0 is equal to 1, and y prime of 0 is equal to 1 as well. All right, so now we need to take a Laplace transform on both sides. We're basically going to try to solve this initial value problem for an unknown g. So that's sort of the big thing. This is unknown. The idea is that later on we're going to choose some g to throw in there, and we'll call that a signal or a control signal or whatever you want. And the idea is that we would like to be able to judge what sort of outputs we're going to get. And if we have a nice way of expressing the solution right from the get-go, we never have to go and try to solve the differential equation a second time. So let's go ahead and take a Laplace transform both sides. And so that's going to leave us with, again, s squared y of s, but this time we don't have 0 initial conditions, so we're going to be left with minus s and minus 1, this one coming from y of 0 and this one coming from y prime of 0, right? So that goes in there. Now we're going to have minus y of s is equal to, say, g of s. We don't know what g of s is. Okay, so now let's go ahead and do our usual work. So we're going to have s squared minus 1 times big Y of s, is equal to g of s plus s plus 1. Okay. Now we're going to divide both sides by s squared minus 1, so we're left with y of s is equal to g of s divided by s squared minus 1 plus s plus 1 divided by s squared minus 1. Okay, now I can do a little simplification. First of all, I'm just going to write this as 1 over s squared minus 1 times g of s. And on the other hand, s squared minus 1 is s plus 1, s minus 1, right? It's an s. We're going to cancel that. It's going to be s minus 1 here. Okay, so now our goal is to write y of t, right? And so this is going to be the inverse Laplace transform of this guy. And so the first term, we're still learning, so I'm just going to write this as s squared, 1 over s squared minus 1 times g of s, and this value at t, plus now we know how to take the inverse Laplace transform of that, and that's just e to the t. Okay, so now we're left with this. How do we figure out the inverse Laplace transform of this term? Well, this is going to be our big F of s, and this is going to be, well, our g of s. Sorry, it already is g of s. Let's go ahead and figure out what f of s would be, or what f would be. So we're trying to figure out inverse Laplace transform of 1 over s squared minus 1. And then we're going to convolve whatever the answer is with g, and then that'll give us that. So, first thing we need to do is we need to take s squared minus 1, and we need to write it as 1 over s plus 1, a over s plus 1 plus b over s minus 1. If I multiply both sides, then we see that we're going to have 1 is equal to a times s minus 1 plus b times s plus 1. Choosing, say, s is equal to 1 gives me 1 is equal to 2b, and s is equal to minus 1 gives me a is equal to 1 is equal to minus 2a. So that tells us that a is equal to minus 1/2 and b is equal to just 1/2. And so that tells us that we have 1 over s squared minus 1 is equal to, say, 1 over 2, say 1 over s minus 1, minus 1 over 2, 1 over s plus 1. I exchanged a and b just because I like having positive things first. Anyway, so what that tells us about this guy is that this is equal to 1/2 of e to the t minus 1/2 of e to the minus t. That's actually Koch? Cinch. I think it's Cinch, right? But I'm not going to write that down. It's just that. So we're not done yet. We actually wanted to figure out what y was. Well, let's see. So first of all, we had this e of t. I'll just throw that out in front just to get that out of the way. But now we have the convolution. So taking the inverse here, this is going to be f convolved with g. Well, that's going to be written as the integral from 0 to t of whatever f was, and we know that is 1/2 of e to the t minus 1/2 of e to the minus t. Maybe I should write this as cinch. That seems a lot easier. Anyway, now this times g of, this is a convolution, right? So it should be minus nu, and then t minus nu here, right? Okay, there we go. Times g of nu, d nu, and then that's it. Okay, so for an unknown g, if we don't know what g is, we can actually cook up a solution, and it is this. Get through this way. By taking a Laplace transform, we have this Laplace transform of g, and we just need to be able to invert whatever this is. The way you invert it is you come back and you do a convolution. And so you convolve the f with g, and this is what you get. And yeah, that's the solution to this differential equation. I'm not sure if they do anything else different. Yep, they just wrote cinch. Okay, so I give in. This can be written as cinch of t minus nu. Right, that is literally a definition, but no real big deal here. Okay, cool. All right, so what other handy things can we do with the convolution theorem? So we have example 2. You want to find the inverse Laplace transform of 1 over s squared plus 1, which would be sine of t, right? But we're throwing in a curveball, we're squaring it. How do you find that? Well, this is a Laplace transform of sine 1 over s squared plus 1 times the Laplace transform of sine. Remember, so we have, just to be clear, Laplace transform of sine of bt is equal to b over s squared plus b squared. All right, so here b is 1, and that tells us that the inverse Laplace transform of that guy squared, put that in a nice obvious place, squared, is equal to the convolution of sine convolved with sine at t, right? And so writing this out is the integral from 0 to t of sine of t minus nu times sine of nu d nu. All right, now if you stop here, and that'd be perfectly fine, I guess. But the reality is, we like to do a little bit more than that. And so something you can do is you can go ahead and you can actually expand this guy. I don't know if I want to do this. Do I want to do this? What am I thinking? Okay, we can expand sine. All right, so just remember, sine of a plus b is equal to sine of a times sine of b, times cosine of b plus sine of b cosine of a, right? That is the sum formula back from good old trigonometry. And so what that means is that, we'll call this star, is that star is equal to the integral from 0 to t. We're going to have sine of t cosine of v minus sine of v using the odd property, cosine of t times sine of v. dv. Okay, so parentheses there, not there. Okay. All right, so if we want to go ahead and expand this out, keep in mind t has nothing to do with v, so we can actually pull it out. So we get sine of t times the integral from 0 to t of sine of v cosine of v minus t has nothing to do with v, so we say cosine of t times the integral from 0 to t of sine of v squared dv. And let's move that little sign over. There we go. Cool. Okay. Take a breath. Okay. So I feel like I'm rushing through this. My children are still down, trying to do this whole lecture at nap time. So I think I'm just hustling through this. In any case, this isn't too bad. So here we can use u substitution, right? So what we can do is we can say u is equal to sine of t, and so then this whole thing, this becomes du in that case. And so this is going to give me sine of t, and then it becomes u squared over 2, right? So sine of t over 2, and then quantity squared. Oops. 2 squared there. And over on the other guy, We have cosine of t, and let's see, sine is converted to 1/2 of 1 minus cosine of 2t, or 2v, my mistake. And this should have been sine of v up here. Then this becomes dv. Yep, looks right. And so now we're left with, say, sine cubed of t over 2 minus cosine of t, and then over 2 times what we get. We get t minus sine of 2t over 2. Yeah. So this would be what you get when you have t here, and when you subtract off what you get at 0, both t and sine of t are 0. Now to keep everything in terms of just t's, just because it's a nice aesthetic, we can change something. So we have t cosine of t over 2, and then minus, say, cosine of t over 2. Sine of 2t is 2 sine times cosine. So actually, this is what we get out of that. It becomes sine of t times cosine squared of t. And I think that's it. Okay. Let's see. Can we do more? I guess that's the question. So there was actually a minus sign here, and that should have distributed through, and so that makes this a plus. And I missed one of my 1/2s, because it would have been 1 and 2 of those, would have made 4. Okay, so that's right. Okay, so now one more thing to do, and then we can match the answer in the book. And let's see. Shoop. Let's do that. There we go. So copy you, and let's go to the next one. And paste. All right, what do we got? All right, so the last key observation here is that if I take out a sine of t out of those two, so I say sine of t times, say, we're going to have sine squared of t, we're going to have cosine squared of t divided by 2, and then we have minus 2 cosine of t over 2. Guess what? These two guys are 1, and so we get sine of t times 1 divided by 2 minus t cosine of t divided by 2. Okay, and that, my friends, is the inverse Laplace transform of 1 over s squared plus 1 quantity squared. All right, now as far as writing it down, I mean, yeah, you could have stopped there in some respects, but honestly, it's kind of unsatisfying, and if it's a multiple choice thing, you're going to want to kind of be able to match the answers. What I did here, all right, so maybe let's start from the top. All right, so the idea was that we want to try to find the inverse Laplace transform of 1 over s squared plus 1 squared. We know the Laplace transform of just one of the individual guys, and what that is it just comes from sine, right? So the Laplace transform of just sine of t gives you 1 over s squared plus 1. The idea then is that if we're going to take the square, is that we want to basically taking the inverse means that we're going to convolve sine with itself, and that has a nice simple expression here. But since these are trigonometric functions, we know we can expand sums using the sine sum formula. And once we do that, we can basically go ahead and evaluate this expression explicitly. And it's not really that bad, it just takes a bit of remembering trigonometry. These were a bunch of really small steps that weren't really all that hard. And so, but at the end of the day, we got this, and that didn't quite match up with what they had in the book, and something seemed kind of off. But if you factor out a sine out of here and a sine out of here, that leaves you a sine squared and a cosine squared. And so then those two terms end up just becoming 1. And so that leaves just a sine. So now it's a nice, simple, closed formula that gives you this. Okay, so that's that. Okay, so this is probably the only thing we really have time left to do, and before my kids wake up, is to solve an integral differential equation. This is a totally different kind of differential equation that we haven't really encountered before, and you can only really do it once you have the Laplace transform and convolution. So they give us y prime of t is equal to 1 minus the integral from 0 to t of y of t minus nu times e to the minus 2 nu d nu. Usually with integral differential equations, they keep y, just is a little bit different. So we write as e to the minus 2 nu minus t times y of t. That's something that you'd, not y of t, y of nu, d nu. And so that's a little bit more usual. So there's all sorts of different things that they would put here, and they call this sort of an integration kernel. So if you change that kernel, you get all sorts of different nice sort of expressions for these sort of differential equations. This is where fractional order differential equations comes from, by the way, which is kind of neat. And I might make a bonus video later on if anybody keeps following the channel after the class is done. We'll see about that. But yeah. In any case, so yeah. Let's go ahead and take a Laplace transform of this and see what happens. I think they gave us one initial value and they told us that y of 0 is equal to 1. Okay, and they want us to go ahead and solve this integral differential equation. Now, what's cool is that we actually can. So keep in mind, this whole term here is just y convolved with e to the minus 2t. So when I swapped it from here to here, all I was doing was taking the fact that we can do convolutions in any order that we want. So now if I take the Laplace transform on both sides, what do I get? Well, I get s times y of s, like we usually would, minus y of 0, is equal to 1 over s, being the Laplace transform of 1, minus the Laplace transform of y convolved with e to the minus 2t. But we know that this is just a Laplace transform, the product of the Laplace transforms. So we get y of s times 1 over s plus 2. All right, and so after that, we just need to solve for y. So we have s plus 1 over s plus 2, and this is times y of s, is equal to 1 over s plus 1. 1 over s plus 1 is 1 plus s over s. And on the other hand, s plus 1 over s plus 2 is s times s plus 2 plus 1 divided by s plus 2, right? So times y of s is equal to 1 plus s over s. All right, now let's do some work. So this is s squared plus 2s plus 1. And now we're going to divide, so we have y of s is equal to 1 plus s over s plus s plus 2 over s squared plus 2s plus 1. We know that this guy is actually s plus 1 quantity squared. And so now this becomes s plus 2 divided by s times s plus 1, because this one of these guys cancel with that guy. Okay, not too bad. All right, now if we're going to solve for y of s, we need to use partial fraction decomposition. By now you should be pros at this. So we're trying to figure out the a and b that will give us this. Let's go ahead and move that to the next page. Okay. So on the next page we have s plus 2 is equal to a s plus 1 plus b s. Right? So s equals 0. It's going to give me 2 is equal to a plus 0, so a is 2. Then we have s is equal to minus 1. That's going to give us 1 is equal to minus b, and so b is equal to -1. Okay, not too bad. All right, so now what do we have? We have that y of s is equal to 2 over s plus, or say minus 1 over s plus 1. And so now that leaves y of t is equal to, say, 2, because we're taking the inverse Laplace transform of 2 over s. The inverse Laplace transform of 1 over s is just 1. And so now that just gives us 2. Minus e to the minus t. And there you go. That's the solution to the integral differential equation. Okay, so that's the basic mechanics of how to use convolution property. The rest of this section starts talking about the transfer function, which is definitely an important thing. I might make a follow-up video if anybody's curious, but it's certainly not something I have time to put on the test. Yeah, so there we go. So I'm going to stop the lecture here, and yeah, we'll go back to my office.
Okay, so that was the convolution theorem, and so hopefully you have a better idea of what that is, and it gives you a new tool to handle solving differential equations with the Laplace transform. Now that's it for my class, and I'll continue uploading a couple other videos if you care to follow me. You know, like, subscribe, you know, that usual YouTube deal. I'll also put up some stuff on numerical analysis because I'm teaching that in the fall, and so over the summer I'm going to be pre-recording a few videos just in case I'm going to have to do this whole online teaching thing again for numerical analysis. I'm probably going to do the same thing for the tomography class I'm going to be teaching. So if you want to learn some more math and numerical methods, that's a place to go. Numerical methods, by the way, include things like the Euler's method that we saw way back in the beginning of the class, and also things like Runge-Kutta, solving PDEs, approximation theory, you know, so generalizing past, say, approximating with Taylor series and things like that. So that's all going to show up on this channel. Yeah, so that'll be fun. Otherwise, thank you for sticking through this with me. This has been a tremendously stressful semester in getting teaching, managing children, you know, trying to write grants, writing papers, working with my graduate students, trying to get homeworks and everything graded for you guys, preparing exams, working with this new format, fielding tons of questions from all of you guys. This has been the most stressful semester I've ever had as far as life management, and so I appreciate you guys giving me a little bit of loosening the leash a bit, I guess. I don't know what I would say there, but in any case, thank you for sticking through it with me. For my class, and this is in spring 2020, you're gonna have your final up in a week. And so this will have about one question maybe from the convolution theorem, and probably not a very complicated one. Otherwise, it's just going to be a cumulative exam from everything. But like I said before, the way I'm regrading it, you know, it actually turns out that you don't actually have to take the final if you're happy with your grade already. So, but yeah, and yeah, we'll see what I do over the summer. But in any case, good luck. And have a great summer, and I hope everybody stays healthy.